Hey everyone, so today we will cover multilingual training and cross-lingual transfer. As you have already learned in this class, there are a lot of low-resource languages that are lagging behind in terms of NLP progress. This is mainly due to the fact that there's not enough data for those languages. For example, this figure shows the number of Wikipedia articles from different languages, and you can see that there are far more low-resource languages on the right that are lagging behind English. And to make matters worse, there's even less annotated data for these low-resource languages. So multilingual training is one of the most effective strategies to improve those low-resource languages. And as we will learn in this class, it also has a lot of other nice properties. So in this class, we will learn about cross-lingual transfer and multilingual training. Then we'll cover zero-shot transfer. And finally, we'll also cover some open problems with multilingual training. So first, let's dive into cross-lingual transfer and multilingual training. Cross-lingual transfer is a very simple approach, but it's very effective for low-resource languages. The basic idea is that we can train a model on a high resource language, for example, from French to English translation. Then using this well-trained model, we can use it to initialize as an initialization point to fine-tune on a smaller data set. For example, Uzbek to English, which doesn't have a lot of data. And using this pre-trained high-resource model to fine-tune on low-resource data is usually quite effective because training on high-resource language provides a good initialization point. However, this approach has a potential problem. That is, if we want to have a model for a lot of different languages and translation direction from many languages to many languages, then for each of the translation direction, we would need to fine-tune one of those models. And for example, here, if we want to support a 4-to-4 translation direction, then we would need to train 12 NMT models in total. And this is not very economic in practice, especially if you want to continuously deploy and maintain these NMT models for the service that you might want to provide. That leads us to the second technique, multilingual training. The idea is also very simple. Basically, you can just use a single encoder-decoder translation model and then just feed data from multiple parallel corpus into the model. So the first multilingual NMT training is proposed by a paper from Google. And in this paper, they simply trained the encoder-decoder model on 5 pairs of languages, and they got pretty good results. But you might want to ask, if I want to translate into many different languages, how does the model know which language I want to translate into? The solution is very simple. You can simply add a language tag at the beginning of your source sentences. So when in your training data, you just add this one tag to your source sentence during training, and then during decoding time, you can just add the same tag to your test data as the language you want to translate into. For example, during test time, you want to translate "how are you" into French. You can just add "to French" in the beginning of your sentence. So now we covered these 2 main paradigms for multilingual methods. Then we want to ask, what is the best way to use those 2 strategies in practice? For example, if we want to train a good model for a new language, what's the best way to do that? Actually, one example use case is a COVID-19 response. So as you can see in this article, it's claiming that COVID-19 is history's biggest translation challenge. This is because the pandemic happened so quickly and it's affecting people all over the world. So it's very important that we get the information we have and translate them into many different languages in a very short amount of time so that people can have access to this shared knowledge. Actually, there's a lot of translation initiatives that try to collect COVID-19 related data in different languages, especially low resource languages and underrepresented languages. And this website has some example data, and it's a joint initiative between CMU and Google, Facebook, and some other big companies. So what is a good way to quickly quickly train a model that can perform well for an unseen language or new language? So this paper from 2018 gives a really good solution. So it basically combines cross-lingual transfer and multilingual training. The method consists of two steps. First, we can do a multilingual pre-training. That is, we train a multilingual model on a mixture of many different languages. So in this paper, they use 58 languages. So this can be done this can be done ahead of time. So you can start, for example, maybe in 2019, you start training this model. And then suddenly in 2020, we are facing this pandemic. You can just use this pre-trained model on many different languages and then quickly fine-tune it on the new low resource language that you want to adapt to. And this method is very effective for many low resource languages and even unseen languages that doesn't exist in your pre-trained data set. So this paper also proposed a very interesting strategy to further improve the fine-tuning. The problem with fine-tuning is that usually the low resource language we have doesn't have a lot of data, and fine-tuning could lead to overfitting. So instead of just fine-tuning on this low resource language, we can pick its related high resource language and fine-tune on both of those data set. So for example, if we want to fine-tune the model on Belarusian to English translation, and there might just be 5,000 sentences in Belarusian, then we can use Russian, which is a closely related language, and fine-tune our multilingual model on both of these data sets. So this figure from the paper shows the model's BLUE score on a low resource language pair with respect to the hours of training. So as we can see, the all to XX models, which means we adapt from a multilingual model, converges really quickly than just training from scratch. And further, we can see that when you're fine-tuning using both the low resource language and its related high resource language, the adaptation performance is usually better. So another fancy approach for training a good initialization model for fast adaptation is to use meta-learning. So in general, meta-learning is a machine learning method that basically learns how to learn. So it usually consists of two optimization loops. In the loop, which would usually optimize for a single task or a single language, and the outer loop would define a meta objective. Here, because we want a good initialization point for all the languages. So the meta objective is that we want to optimize how quickly our model is able to adapt to each of these languages. And this figure shows some intuitive explanation of transfer learning, multilingual learning, and meta-learning. So as we can see in figure A, transfer learning aims to adapt from a pre-trained model to each of the individual language. And in multilingual transfer learning, we are training a multilingual model on many different languages and then adapt to each of the individual language. And in meta-learning, we are moving this model initialization point closer to each of the languages. So during adaptation time, it's going to be faster and easier. So now we've covered cross-lingual transfer and multilingual training, and we'll move. And next we will move on to zero-shot transfer. Zero-shot transfer, intuitively, it means that we want to train a model that works for a language during test time without training on annotated data in that language. Well, of course, you are allowed to use monolingual data for the language or annotated data from other languages. So for example, you want to train a model that can do sequence labeling for Belarusian. So then you are given monolingual data in Belarusian or sequence labeling data in English. However, you won't be able to have sequence labeling data in Belarusian. So just using monolingual data and annotated data for English to train this, then you should be able to adapt this model to Belarusian without seeing any sequence labeling data in Belarusian. Well, first, let's focus on zero-shot machine translation. So zero-shot machine translation is a very useful concept because in practice, a lot of the parallel data we have are English-centric. So zero-shot for machine translation has its own unique definition. So for example, we want to translate from Zulu, which is a language in Africa, into Italian. But since a lot of the parallel data are English-centric, we would have maybe a little bit parallel data between Zulu and English. And we'll probably have a lot of parallel data from Italian to English because Italian is a relatively high resource language. But unfortunately, there won't be any Zulu to Italian parallel data. So although we have access to some Zulu data and Italian data, but since there's no parallel data between Zulu and Italian, this would still be considered as a zero-shot scenario for neural MT. But how are we going to translate from Zulu to Italian without parallel data? Multilingual MT is actually a very natural solution for this problem. So as we have learned, during training time, we have Zulu to English, Italian to English parallel data, and we can just train our multilingual model on these data sets with a target language tag added to each of the source sentence, indicating which language the parallel data is translating into. And during test time, if we have a Zulu source sentence, we can just add two Italian tag to the Zulu sentence. Then it will be able to translate into Italian. However, as you can see that this zero-shot transfer performance might not perform as good as if you have parallel data from Zulu to Italian. So there are a lot of strategies to improve zero-shot transfer performance. One method is to use extra monolingual data. So for example, if you have monolingual data from Italian, you can still add it during your multilingual NMT training. The way you can add it, the one strategy to add it during training is you add a noise version of your Italian data to the source, and then ask the NMT model to reconstruct the original Italian sentence. So this is called a masked language model objective, and it is shown to greatly improve the zero-shot transfer performance for multilingual models. So there's also another strategy to help encourage zero-shot transfer. So as you can imagine, zero-shot transfer is possible for multilingual NMT models, probably because we are training on many different languages, and the model somehow learned a language universal representation. So when you feed a source sentence into the encoder, maybe the encoder is able to encode the source sentence into a representation of the meaning of the sentence, which is universal for different languages. However, zero-shot transfer might not work so well for the standard multilingual training, probably because there's not a very strict supervision of this universal representation. So in this paper, the authors proposed to add a direct supervision to encourage this language invariant representation. So the way they do that is for each source to target parallel sentence, they feed both the source and the target into the encoder and add a similarity loss between these two representations. So the idea is that we want the encoder to encode sentences from different languages that have the same meaning to the same space. So now we covered zero-shot transfer for NeuralMT. It is also very useful. It is a very useful technique for transfer for pre-trained representation. So in this paper from 2019, the authors found that multilingual representations can be used for zero-shot transfer for many downstream tasks. So the strategy that they do this is, first they train a large language model using only monolingual data from many different languages. Then you can use annotated data, for example, NER data in a given language, say English, for example. But during test time, you want to test the fine-tuned model on some other languages other than English, for example, French. So during training and fine-tuning, you don't have access to sequence labeling or NER label for French. But during test time, you would be able to use this pre-trained and fine-tuned model on NER tagging for French. So this is possible because during pre-training stage, multilingual pre-training can learn a language universal representation. So when you adapt the model using English, it's also able to do a similar task in French. And you might think that this is because English and French has a lot of shared vocabularies. So maybe adapting using English is somehow also very helpful for French. But this paper also does an interesting analysis which shows otherwise. So in this figure, it shows the zero-shot F1 score of NER in different languages, and the x-axis shows the vocabulary overlap between the language that we fine-tune the model on and the language that we test. So as you can see, with just 0% of vocabulary overlap, we can still get a pretty good zero-shot F1 score. So this means that somehow this multilingual pre-training can generalize to languages with different scripts. However, this paper also shows that it does not work very well for typologically different language. So for example, if you fine-tune the model on English, it won't perform as well on Japanese. Now we've covered zero-shot transfer, and we will finally move into some open problems with multilingual training. So recently, people have been very interested in massively multilingual training. So in essentially, what they want to do is that they want to scale the number of languages supported by Neural NMT to up to 100. So we've seen the first paper on cross-lingual multilingual training use about 5 pairs of languages, and then the fast adaptation method pre-train multilingual model on 58 pairs of languages. And here they want to scale it to over 100 languages. So in the multilingual training setting, there are usually 3 settings that people test. Many to one, which means we translate from many languages into one language. So if we translate from 100 languages into one language, that means we have 100 to 1 translation direction. And 1 to many means that we translate from a single language into many different languages. And many to many means we translate from many languages into many different languages. So if we want to support translation from 100 languages into 100 languages, using just a single model, that would save a lot of model maintenance effort. So one problem with multilingual training, again, is the data distribution over language pairs are highly imbalanced. So this figure is from the paper from Google in 2019, and they can show us the exact number of the resources they have. But we can see that even Google has a very highly imbalanced data set. They might have a data for those high resource languages, they really do have a lot of data. But for a lot of low resource languages, the number of data they have is still limited. So improving low resource languages and multilingual training is actually a very relevant problem, not only in academia, but also in industry. So if we want to train such a big multilingual model on 100 languages, we have to take into account that the data set size are not uniformly distributed among different languages. So a very necessary step to do is to upsample those low resource languages during training so their performance can be competitive. So a very standard approach that's used in this paper is to sample data based on the size of the data set. So they use a temperature term to define this probability distribution over all the data set or all the language pairs they have. So a temperature of 1 means that you would sample data proportional to the size of the data set. And temperature of 5 is a middle ground between uniformly using data from all the languages or just use a lot of data from high resource language and very little data from low resource language. So in the paper, they usually use a heuristic temperature to control this upsampling ratio. but it is possible that the heuristic is not perfect. So in this paper from this year, the author proposed a method to learn to balance training data from different languages. So basically, they are defining they're still using the data sampling distribution over the data set during training, but they try to optimize this distribution throughout training process so that the model's performance on all the language pairs are optimized. So the general idea is that during training, after training on the data set for a few steps, you can take a look at the model's gradient on each of the training data set and the model's gradient on the multilingual data set. And then the method would learn to equate the training data set that has similar gradient with a multilingual data set. So this is built upon the assumption that you want to favor the language or the data that helps move the model's parameter that can improve the performance on all the languages you care about. Next, we will talk about some still open problems in multilingual NMT. The first problem that's been widely studied is that multilingual models tend to perform worse than just training on a single pair of language for those high resource languages. So these two figures are taken from the paper from Google. And the figure on the left is many to one translation, and the figure on the right is one to many translation. And the x-axis lists the performance of the x-axis lists the performance of languages. The x-axis lists the language from high resource to low resource, and the y-axis just shows the difference between the multilingual model and a model that trained on a single pair of language. And as we can see in both settings, high resource language tend to have a negative improvement than the baseline, while the low resource language really benefit from multilingual training. This is a problem for a multilingual model, especially if you don't want to degrade the performance on the high resource languages, which potentially is used by a lot of speakers. So some possible solutions are first, instead of training a single multilingual model, maybe we can train one model for each language cluster. So instead of using 100 languages, maybe we can just use 5 languages or 10 languages that are very similar. Second, pretty easy approach, or not easy, is to make the model bigger and deeper. However, it's not as straightforward as it sounds because it increases the training cost, and bigger model also has many instabilities during optimization. And third approach is, again, maybe you can use some extra monolingual data during multilingual training. So this paper actually proposed a very interesting idea for this multilingual training issue. They use a technique called knowledge distillation, which means that first you can train a teacher model, and then using the teacher model, you can use the teacher model to better train a new model from scratch. So instead of so during NMT training, instead of optimizing the model's cross entropy loss, on parallel sentence pairs, you use you try to match the student model's distribution over the vocabulary with the teacher model's predicted distribution over all the vocabulary. So in this way, instead of relying on the parallel data only, you are taking advantage of the you are taking advantage of a pre-trained model. So in this paper, they found that if you train each of the individual model on each language pair, for example, you can train 3 models, each from French to English, Chinese to English, or Zulu to English, and then you can distill all these models into a single multilingual model. And this would make the multilingual model better outperform each of the teacher model that you trained on. So one possible explanation for this is that the multilingual model is able to better exploit the representation for each of the parallel language pair. However, this approach also is not very practical because it takes a lot of effort to train many different models. And another approach to address this issue is to have a language-specific layer in a multilingual model. So if we want to preserve the multilingual model's performance on each language pair using a single model, we are probably going to run into some model capacity issue because each of the language pair is going to fight for the model's capacity to learn its representation. So in this paper, they add a language-independent layer for each language pair on top of a single multilingual model. So it could better, so these language-specific adapters are able to capture the specific representations for each language pair while allowing the multilingual model to learn a language universal representation. So the second problem with multilingual model is that one-to-many translation direction is much harder to benefit from transfer learning than many-to-one translation. So again, this is a figure we have seen before. And here we have high resource languages on the left of the axis and low resource language on the right of the axis. And we can see that in both cases, a low resource language tend to benefit from multilingual training. But it's very clear that in the any to English translation or the figure on the left, the low resource languages has a way higher improvement than the figure on the right. So this is probably because one-to-many is more like a multitask problem than a many-to-one translation, because here you are having a single decoder that tries to generate sentences into many different languages. While for the many-to-one setting, the decoder only needs to generate into a single language. So the NMT model only needs to learn a representation, language universal representation, and the task for the decoder is much easier. And it's, so how can we help improving the transfer learning for one-to-many setting? Maybe we can add a language-specific module, or maybe we would have to design a better strategy to decide what parameter to share and how to separate the model for each of the language. So how to maximize the sharing between these languages while giving each of the language pair enough capacity to model their own characteristics. So this is still a pretty hard problem. And it's a hard and open problem for multilingual training. Another open problem is that multilingual vocabulary construction is not is probably not optimal for our current strategy. So the standard approach is we combine all the languages together and then learn a joint vocabulary on all the data. So we need to learn a joint BPE. Sorry, there's a typo. It should be BPE instead of BPT. So BPE, as you probably already learned from machine translation class, it learns a word segmentation of the data we have. So it can construct a vocabulary of limited size for the model to predict. However, if we are trying to translate sentences into many different languages or languages with very different scripts and vocabularies, then the standard BPE algorithm might learn to favor some high resource language while over-segmenting the low resource language. Standard approach is, again, we upsample those low resource language data before learning a BPE jointly on all the data. But this is still a heuristic approach, and it's not super clear what is a better approach than that, or how much morphologically rich language suffer from this joint BPE problem. And it is likely that as we scale up to many more languages, the BPE problem, non-optimal segmentation is going to be a huge problem for the low resource languages. And finally, another problem for multilingual training is that it is also not clear to what is the best strategy to evaluate the model. So now we probably, the very intuitive approach is to use average BLEU score for all the languages. But even then, we will still face with a problem where two systems have the same average BLEU score, while one perform better for some language pairs and the other perform better for some other language pairs. So in this case, it's hard to decide which one is better. And second, BLEU score itself might not be a good strategy to calibrate multilingual model, because when the BLEU score between two languages might not even be comparable. So you might have 0.5 BLEU score on English Chinese, but it doesn't necessarily mean that it will have the same benefit as a 0.5 BLEU score on English French. So it's hard to calibrate the absolute quality improvement between different language pairs using BLEU score. So for the discussion question for today is to think about an interesting problem with multilingual NMT. And specifically, you can read this massively multilingual neural machine translation paper from Google. I think it gives a really good overview and existing problems with multilingual NMT. So you can just read this paper and think about one problem that you're interested in, and maybe come up with your own solution or summarize the solution provided in the paper.